All right. Well, how's it going, everybody? Well,
let me make sure.
How's it going, everybody?
Set up
well
properly.
All right. Cool. Let's see. We're in the nice. All right. Cool. So let's see. All right. Cool. Okay. Hopefully everybody is having an awesome time coming back to class after an excellent spring break. That is, I hope you had an excellent spring break. If you didn't, then you're probably happy to be back in classes. And if you did have an excellent spring break, then my condolences. And also congratulations. So we're going to learn a little bit more complex analysis. Hopefully that first exam was not too ridiculously brutal. I think it seems like a fair number of people have turned it in already. Similarly fair number of people have also opted to utilize all of their time to complete the exam, including today. I imagine I will get a flood of exams at around 11:50 tonight. We'll see. That's fine. I totally get it. I did the same thing. And I hope they're not too bad. If you're going to email me asking any questions or for any clarifications, please don't do it at 11:15. Do it a little bit earlier, and you'll have a non-zero likelihood of me replying in time for you to submit the exam. But enough about that. Anyway, let's get into it. We're going to talk a little bit in chapter 3 about series representations of analytic functions, thereby, earning the name analytic, at least in terms of how it is frequently used. It'll be pretty cool. The kind of general idea of the whole thing is just basically what you did in Calculus 2. Right? I mean, it's nothing special. Chapter 3 is all about the big idea is to write analytic functions as, I'll put it in quotes, infinitely long polynomials, basically, in some appropriate region where this makes sense. Then, after we discuss how to do this, we're going to talk a little bit about some mild extensions. That is, we might want to write some function f of z in terms of some infinite series, say k equals 0 on out, of some I'll just write it like this. We'll do this slightly differently, but just think of it like this, right? AKZK, right? Some coefficients and some powers of z. Let's write it out like that. All right, cool. Some people may be objecting and being like, but what about Maclaurin series, Taylor series? Put that all aside. Just think about long polynomial, kind of the idea for this loose introduction. We'll start by looking at things like this, and then we'll get to, hey, well, if we got something good here that makes sense in a certain way, then what about the things where this doesn't quite hold for, things where maybe you have, undefined values at certain points. Functions like 1 over z, or even easier, what about z over z? Like, that's not exactly analytic. It's not an entire function. It's not even defined everywhere, right? But it's 1 everywhere except for 0, right? So it's really close. it feels like we should be able to borrow basically everything from the entire function f of z equals 1, right, for the function z over z, and what gives. And so what we're going to end up doing is we're going to do a cool trick, and this will lead us into talking about meromorphic functions instead of holomorphic functions. These are it's basically the same kind of thing we've been dealing with, but with certain ways of classifying the ways that you can fail to have analyticity or be defined at certain points. Kind of, it'll turn out to be pretty mild and kind of comprehensible, hopefully. But the big idea just comes down to saying, hey, what if instead of starting at k equals 0, I started at k equals like -1? Or what if I started at k equals -2 or -3? Or what if I went from negative infinity to positive infinity, right? And did a double direction sort of infinite series like that. And that will give us a variety of different notions of what it means to be analytic, to be meromorphic, and or what it means to be not defined at certain points. Poles, we'll talk about the order of zeros, things like that, removable singularities, essential singularities, and we'll even get to, at the end of the chapter, one of my favorite theorems in all of complex analysis. It is a hell of a theorem. The Kasarati Weierstrass theorem. It is one of the first times when I first took complex analysis, I remember going, oh, holy shit. Like that is an amazing result. That is crazy. We'll state it in its more boring form initially, and you'll probably be like, Bryce, what's wrong with you? And then at just the conclusion of this chapter, we'll talk about the cool form of it, and you'll go, oh, whoa, that is something else. So to begin chapter 3, we're going to have to talk about convergent series. This will build a lot of things off of our Calc 2 knowledge, and it starts out slow, so don't worry. I had to take a drink of my delicious 0 sugar 7-Up right here. Don't worry, it starts out relatively slow. It's not going to get brutal or anything. The beginning of it, though, while kind of technical, is quite important. And if you don't remember these things too well from Calculus 2, I highly encourage you to go back and review some of your past work with infinite series and this kind of thing. Some of the classic tests. We'll talk about them again here, but it never hurts to do some exercises. So I encourage you to look back at some of your prior knowledge. So to begin, we're gonna do a quick definition. So a sequence, Zn for n equals 1, 2, 3, on and on, right? A sequence of complex numbers indexed by the non-zero integer, positive integers, the naturals or something, depending on whether you want to include 0 in there. This is said to converge, so get close to, some complex number, let's call it z0, if for each epsilon greater than 0, there is some integer, capital N, such that for all little n bigger than or equal to capital N, we have Zn minus Z0 less than epsilon in modulus. So the kind of idea here is exactly the same as what you did back when you were talking about sequences of real numbers converging to a real number in Calculus 2, this kind of thing. I think I have to adjust my microphone. Nothing particularly fancy is going on or anything like that. It's just something we've already covered before, I believe in chapter 1, maybe in section 4. This is just the idea that, hey, if in modulus, the measurement of distance in the complex plane, the elements of the sequence get close to some value, as close as you want, in fact, and they stay close, then they go to it. And that's what we're going to say, or they converge to it. And the way we denote convergence of Zn to Z0 is by Zn right arrow Z0. Okay. Naturally, we can use this notion of pointwise convergence to build for ourselves a notion of convergence for infinite series. So an infinite series of complex numbers converges when the sequence of partial sums converges. So if you write Sn, that's the sum from k equals 1 up to n of the terms of your sequence or your series. If these guys define a sequence in the sense that we've described up here that converges to some value, let's call it big S, then we'll write that this infinite series is equal to S. That is, the sequence of partial sums get close to the eventual limiting value, right? Okay, cool. So, as with real series, a complex series converges absolutely if it converges in modulus as opposed to, in this case, or in the real case, absolute value. And we can use the Koshi criterion for series, which, if you don't remember, the Koshi criterion for series is a classic old result, which, well, here, let's just say this next result, and then we can get on to, we can talk about that briefly. But the following proposition can be derived from the Koshi criterion for series. It says that if a sequence of complex numbers converges, or a series of complex numbers converges absolutely, then it also converges. So this says that absolute convergence implies convergence. This is very important because absolute convergence allows us to use all of our things from calculus 2. That is, the sequence of the sum of the moduli of these complex numbers. This is a real series, right? So the usual tests for real series apply. Kind of cool. All right, nice. So this gives us all of our good usual series tests. By the way, if everyone remembers, sorry, one second. My apologies. Oh, if everyone remembers their series stuff very well, anyone who does remember their series stuff very well, feel free to just fully tune out this piece right here, since we'll just cover things you've already heard. But if you don't, we'll do a very brief refresher. So proposition 3.13 tells us the following, a bunch of things from calculus 2. First one is that geometric series. So if you have a r in modulus less than 1, then the sum from n equals 0 to infinity of r to the n converges to 1 over 1 minus r. Okay. And it diverges if r is bigger than 1 or equal to 1 in modulus. Fair enough. All right, easy. It says if you take something less than 1 and you take a bunch of powers and you add them up, then you end up converging. If you sum a bunch of things that are bigger than 1 in modulus, then you definitely don't converge. Yeah, fair enough. So the comparison test is another good one. That's the geometric series just formula. The comparison test is actually a test. So if you have a series, the sum from k is 1 to infinity of bk, and if this guy converges and ak is less than bk for all k and bigger than 0, right? Because otherwise you could just, have everything be crazy and negative or something like that. Then the sum from k equals 1 to infinity of ak, that series, also converges. That is, if you have every term of the series bounded by a term in a series that you know converges, then you can't diverge in any particular way, as long as you're bounded in a sensible way, right? Similarly, you can do the opposite. If you have a divergent series, the sum from k is 1 to infinity of ck, this guy, if this diverges, and you have another series in terms of dk's, and the dk's are all bigger than the ck's, which are bigger than 0, then that guy diverges as well. So basically it says that, hey, if you're bounded above, if every term is bounded by the terms of a convergent series, then you have a convergent series. And if each term in your series is bounded below by the terms of a divergent series, then you have a divergent series. You're just comparing series. All right. Then we have the p-series test. So p-series are a particular nice form of series. They're series with the form the sum from n equals 1 to infinity of n to the minus p. Okay. These guys converge if p is greater than 1, and diverge to infinity, that is, it grows very large, if p is greater or is less than or equal to 1. Sensible. You can also write it without the minus sign, and then you can, of course, change your definition accordingly, or the statement of the theorem accordingly. The ratio test is another classic one. So in this case, we look at the ratio in modulus of successive terms in your series, so an plus 1 over an in modulus, and you take the limit of this. If this exists and is strictly less than 1, then the series, sum from n equals 1 to infinity of a sub n, converges absolutely. That's a big old deal. The absolute piece is nice. If the limit is strictly greater than 1, the series diverges, and if the limit is equal to 1, it's inconclusive. You can't say anything. You have to use something else. All right, cool. Then there is finally the root test. In this case, we are supposing, similarly to the ratio test, we are looking at a limit involving the terms of the series. In this case, if the limit as n goes to infinity of a sub n in modulus to the 1 over n exists and is strictly less than 1 once again, then the series defined by these a sub n converges absolutely. If the limit is strictly if it's strictly greater than 1, it diverges, and if it equals 1, then it's inconclusive yet again. So hopefully this has been a nice refresher of some basic results from Calculus 2. If you do not recall these that well, I encourage you to go look back at your notes or your Calc 2 textbook. In particular, you might find it helpful to review some other criteria, for example, like the integral test or something like that. We won't talk about that here. It won't come up too much, but these are good things to remember. All right, cool. So, my apologies, the scan here is not particularly great. So, up next, we're going to get into talking a little bit about how functions can converge as opposed to points. So, sequences of points can converge to a point, a specific value. How about a sequence of functions? Can it converge to a specific function? Yeah, of course it can, but it can do so in a variety of different ways. And this is an important distinction that I think trips people up sometimes. So this is the notion of uniform convergence. All right, so uniform convergence is kind of what we're gonna have to spend a little bit of time on here because it's worthwhile to talk about. So, let me make sure I got everything set up here. All right, so we've got a sequence of functions fn from some domain A into C, all defined on the same set A. Okay. We're going to say that the sequence converges pointwise if for each value z in A, the sequence of points fn of z converges. That is, if you evaluate each function in this sequence of functions at the given point, it converges to a some value, right? Okay. This limit defines a new function, f of z, on A. The obvious way to do this is that f of z is equal to the limit as n goes to infinity of fn of z, right? Oh, okay. Kind of nice. That makes sense. So this is a sequence of points, and if we're saying, hey, if these guys converge, then we can get a new function out of it. Sensible. But this is a pointwise notion of convergence. That is, the limit is being taken over the values that you get out, as opposed to over the functions themselves in a certain way. And this can lead to some behavior that you don't want. So the picture here that we'll think about is something like a parabola that slowly widens out. I'll draw this in a moment. And the kind of idea is that if you just keep widening a parabola out, eventually it'll flatten down to zero, right? In the limit or something. But it'll take the outside edges of it a very long time to get all that close to zero. Okay. So I'll write this down more formally. But that's sort of the gist, is just that we want to talk about when an entire function, not entire in the sense of complex, but the whole function gets close to another function, not just the points that get passed to the sequence of functions gets close to a value each individually, but when do sequences of functions get close to some function all at once? And this is the notion of uniform convergence. So let's define it. A sequence Fn of functions from some domain A into the complex plane, same setup as before. We say that this converges uniformly to a function f if, for every epsilon greater than 0, there is some big N such that for little n greater than or equal to big N, the nth term of this sequence evaluated at z minus f of z is less than epsilon in modulus for all z in your domain. Okay, so the idea here is that you're sticking in like a little band, right? The nth one never gets more than an epsilon away from your function, right? So the difference here, this distance from above, like the furthest it ever gets, is never more than epsilon in either direction, above or below, something like that. And so, if they just keep getting closer and closer, then that's uniform convergence. This is as opposed to something like, let me draw a little picture. Say you had something like Fn of z is something like 1 over n z squared. That's a bad 2. So you can think of these like we've got like a parabola, and then you kind of widen out a little bit, and then you widen out some more, and more and more and more and more, so on, right? Okay, fair enough. And in the limit, you can imagine that you just get, a flat line, right? Okay. So very obviously, in a pointwise sense, it converges pointwise, but it doesn't converge uniformly, because if you look in some epsilon window around this function you eventually get to here, this constant one, you always have stuff that's outside of it. That shouldn't have used a dash line there because I have to press undo too many times. That is, if I zoom in a little bit here, notice while I might be able to stay with an epsilon close by, everything is pretty close to it. The further out I go, notice everything's getting really far away. And in fact, for some of these guys, like the blue one, just imagine how freaking high up it would be over here, right? You can't even really draw it in. It would be way like off the screen, off, out of my house high. So that is the kind of thing where you don't get uniform convergence. The way to think about it is that there's like a uniform speed of convergence, right? Like the things in the center here get close to zero pretty quick, right? For relatively small values of n, they get pretty dang close to zero, right? To this eventual limit. And the stuff that's further away from zero, it takes a lot longer. So there's no uniform speed. right? Stuff in the middle gets close quickly, stuff far away gets close slower and slower and slower, and there's no kind of upper bound to it. And this is what pointwise convergence is all about. It's about having these little epsilon bands that let you close in on your target function, on the limiting function. So that is a lot more restrictive form of convergence, and it will allow us to do a lot of nice things. So, of course, we can build series that define functions by using this notion. So a series, the sum from k equals 1 to infinity of g sub k of z, is said to converge pointwise in the same sense as we were talking about up here, if the corresponding sequence of partial sums, Sn of z, which is just defined by the first n terms of this series, converges pointwise. Okay. You can also do exactly the same thing with uniform convergence. So you can look at this guy and talk about uniform convergence if the sequence of partial sums, these functions, converges uniformly to a given function. All right, so it can totally be the case that a series converges pointwise but not uniformly. But can it be the case that a series converges uniformly but not pointwise? Think about it for a second, and you'll see pretty quickly that the answer has to be no. Uniform convergence is pointwise convergence plus. It's the premium subscription only version of pointwise convergence. It's the good one, right? It's the one you want. So this is what we'll need to use this sometimes, and this will give us a lot of things. In particular, the Koshi Criterion will come in handy when talking about series representations of holomorphic, analytic, complex differentiable with Cauchy-Riemann functions. So Theorem 3.1.5, the Koshi Criterion, has two little pieces. The first one says that a sequence, Fn of z, converges uniformly on a set A. Remember, all of the uniform convergence is relative to the domain of the functions here, right? So your function might be defined, the function f might be defined for a bigger set than A, but if your sequence is only living on A, then you can really only converge to something that's defined in the domain that makes sense for these guys, right? Maybe not. There is a notion where we can talk about, we'll get to this in the beginning of chapter 6, where being defined locally maybe has enough to tell you something about the global function. But for now, obviously, we're doing everything relative to a domain. So a sequence Fn of z, these sequence of functions, converges uniformly on a domain A if and only if for each epsilon greater than 0, there is a capital N such that for all little n greater than or equal to big N, in modulus Fn of z minus f of n plus p of z is less than epsilon for all z in A, and all p in 1, 2, 3, 4, and so on, right? So this says that uniform convergence can be determined by whether or not, everything eventually gets close and stays close, right? Fair enough. At every point. And then we have that a series, the second part, a series from 1 to infinity of gk of z converges uniformly on A if and only if for every epsilon greater than 0, there is a big N such that for all little n greater than or equal to big N, the sum in modulus from k equals n plus 1 to n plus p of gk of z is less than epsilon for all z in A and all p in 1, 2, 3, so on. Notice the first one immediately gives you the second one, since when you take the difference of two sequences of partial sums, you just cut off the first n terms if it's like fn plus p, right? Does that make sense? It's this guy right here is equal to the sum from k equals 0 to n plus, I'll just write it like this, n plus p of gk of z minus the sum from k equals 0 to n of gk of z, right? And notice, since we're in modulus, we could flip these two around and you would just get the same thing right up here. Yeah? Okay, so the second one is just the series restatement of the first one. Nothing too fancy. So this is the Koshi Criterion, and it will come in handy. Basically, all we're doing is we're saying, hey, we need to have a not too much oscillation, a bounded oscillation, eventually zero oscillation. Things can't bounce around too much, kind of like in this picture right here. This function's like oscillating around the other one, and the oscillation has to get kind of small. That's what it's saying, and it has to stay small. So there's a more technical way to say it in terms of oscillation, but for all physical intuition intents and purposes, that's all you have to really think of, is that you might be wiggling around this eventual function that you're going to get to, but you don't wiggle too much, and that wiggling just gets smaller and smaller, right? Okay, cool. And not only does it get smaller and smaller, but the successive terms of the approximation wiggle around each other less, right? So that's kind of the way to think about it. And what we'll get to is a nice little proposition, our first kind of maybe non-trivial sort of result in here. Not that these things, I don't want to say these other things are trivial, but they're more like Calc 2 sort of stuff. So proposition 3.1.6, if the sequence fn of functions indexed by n consists of continuous functions defined on a set A, and if fn goes to f uniformly on A, then this limit is continuous on A. Okay, so the uniform limit of continuous functions is continuous. That is, uniform convergence preserves continuity. It's probably a pretty good hint that this is a good type of convergence. Is this true for pointwise convergence? It's a tough question, right? Now, all you'd really have to do is come up with a sequence of continuous functions that converges to something discontinuous to prove that the same does not hold for pointwise convergence, and that's quite easy to do. So here's a great example. So you could form look at some function like this, and we could just we can make a sequence of functions just by, I'm going to slightly draw this underneath so you can sort of see the difference, right? And oops, I think I made one of, yeah, it's close enough. And all we're going to do is we're going to make this a little bit steeper every time, right? So we could just keep doing the same thing and getting a little bit steeper. And obviously, as we keep going, right, what will we eventually converge to? Well, it'll just be the function, and I'll just draw it down here. It'll be a function that looks like this. It'll be a function that looks like that. And sorry, to be clear, these are living in separate worlds, right? That's what I'm trying to say. So these guys converge to that guy, the function that just isn't defined and has a big jump right there. You see what I'm saying? So you have this sequence of continuous functions, and they converge pointwise at least, to something that, oh my god, it isn't even continuous. It's even defined at a certain point. Or you could make it so it's like defined like here or something, or like, you know, open right down there, right? So, you know, you can have pointwise convergence that doesn't preserve continuity in a nice way. However, for uniform convergence, we preserve continuity. So a sequence of continuous functions converging uniformly to some function, well, that limiting function is also continuous. And so it's a heck of a thing, and a very, very useful feature of uniform continuity, and why we care about it here. After all, if we're going to talk at all about, you know, some sort of differentiability and stuff like that, analyticity, continuity is just that's like the base requirement. You know, you can't even get in the door of the analytic club if you're not continuous. It's like a dress code. So second part of the proposition, if the functions gk of z are continuous and g of z is equal to the value of the series of these gk's, that is the sum from k is 1 to infinity of gk of z, which exists if you have the sequence of partial sums converging. But in what form? If it converges uniformly on A, then G is also continuous on A. Okay, so this says it's exactly the same as the beginning part, just that the uniform limit of continuous functions is continuous. And so naturally, since a series is defined in terms of a limit of partial sums, right? If the series exists, if it converges, right? Then uniform convergence, of course, brings through the properties of the terms of the series, in particular continuity, because the sum of continuous functions is continuous. You bring this right on through. All right, easy enough, cool. So this is our first hint at why we have to care so much about uniform convergence. It preserves continuity in terms of sequences of continuous functions, and of course that carries through to give us continuity of series whose terms are continuous functions. Okay, now we're gonna keep going, and I might actually I'll probably end this one right here, but since people have exams to finish tonight, and we're pretty close. Next time we'll start by proving the Weierstrass M-test. This will be a useful test. I believe we may have, depending on who you took Calc 2 from, you may have covered this. You also may not have. So we'll prove it. And in particular, since we're in the complex plane now, it's worth reproving anyway, because it's not as trivial as some of these other things we've talked about that we're all familiar with from Calculus 2, since we may be interested in something other than absolute convergence or something like that. So we'll begin with the Weierstrass M-test, and we'll do a lot more stuff with talking about integrals and interchanging sums and integrals, which if you can imagine thinking about, say, like a Taylor series defined in terms of derivatives and all that sort of stuff, thinking about Koshi's theorem and the way we get formulas for derivatives in terms of integrals, it may be sensible to talk about when we can interchange a big sum and a integral. So that will help us. Then we'll get into the analytic convergence theorem and talk about the appropriate domains for things to converge. And hey, look at this. We're going to see some nice pieces involving Koshi's theorem. And this will build all the way up to the end of the section. And in the next section, we will talk about series representations of analytic functions. Kind of cool. And I guess I will leave you there for tonight. Let's call it quits and give everyone a few extra minutes to work on exams. If you have any questions, as I said earlier, please remember to email me. All right, cool. I just realized I left my music playing for the entire lecture. I hope that wasn't too distracting. Oops. All right. Well, have a great night. Bye.